Okay, see, in the last lecture we basically described a short crested, or we can say same as where, or one can say directional wave spectrum is all the same term. Obviously, we are only defining that because our full idea is to study how the shape would respond in that, okay, the response in that. Now, obviously, today we have to talk of response, but before I go back to this, I wanted to show you a little bit of this diagram, see, which would make it little more clear to you about this way the directional spectrum is plotted. See here, I have this side the omega or f, this is my minus 90 to plus 90 frequency, the directional spread. So, this graph, if I look at this graph, this is my f theta, absolutely, this is my f theta, and of course, this side is my s omega. You can see this bell shape is so evident, right. And if I take excuse me, volume under that, actually it will become still area unit wise, because remember this side has no unit, this degree, this is my top is still going to be meter square second, because you know meter square second into, well no, yeah, into here 1 by second into no dimension gives a meter square, the same thing. So, although we call volume, remember one of the integration is over d theta, which is dimensionless. This side has no dimension, remember this side is having a dimension of radian per second. So, this side dimension is meter square second. Okay. This is how, just to give you a feel about that, but about the 3D spectrum, because difficult to plot it, but I will tell you that this is another diagram which actually is the plot for a 3D spectrum as measured from some data, that is for a typical C. So, for a particular C for which the wave slope information or the directional spread was known, you know, somebody has collected the actual data, looks like that. Why I am showing that? Because you will again understand here, see, when he projected this side, if you are going to project this side, what you find here is supposed to be this s omega at theta equal to 0, because you know if you project just like that, if I were to project this side view, then what I will get is s omega in 2D, and this side if I project, I should get a spread. You see here in this particular case there is a peak here, of course this particular C data appears to have 2 peaks. This might have been for a typical you know data that obtained to a typical C, which is typically not so. Just this is an example, but what you find out is that there is a concentration, it is still, the entire thing is still like a bell curve, excepting that in this particular data it happened to have 2 peaks, but normally you would have 1 peak type. So, you know this is how it looks like. Okay. So, now we will get back to our motions in directional C. So, of course, what we found out is very interestingly is that S3D no, not omega, this is omega, sorry, let me again write it, sorry. I am writing omega as this thing, mu or theta, what you call it, let me call it now wave, because we are going to have also ship angle coming. So, this we knew that, right. Now, we have this ship coming. So, let us look at some kind of diagram here to know this angle business before. Let us put some inertial reference. So, I have now here the ship going, say, okay, and my dominant wave direction, let us say this is my dominant wave direction. Okay. So, which side the waves are? Waves are essentially the entire waves according to my spread is lies between this sector, that is coming from here up to here with the dominant wave this side. So, what is happening? This ship is going to therefore feel waves right from this angle, the wave coming here, right to wave coming here. Now, this is my of course dominant wave, well, let me call this dominant wave direction to be some with number star, and in general wave direction, any general wave direction is going to be this mu w. So, my wave heading of the ship is this angle, or this is the angle which that will be between the wave direction and the ship direction. See, this was a dominant wave direction, I said okay fine, and any wave direction if you take any wave direction, this is going to be this, and of course the heading angle is nothing but, what is the heading angle? The difference between wind direction, wave direction and the ship direction. So, wave heading, actually the ship's heading mu, which is what the heading angle we call, basically is nothing but mu w minus mu s. That is the wave heading angle, is not it? Now, of course, if I talk about the dominant direction wave heading angle, it is going to be this. Now, what is happening? See here, excuse me, this is my wave heading angle. Now, dominant direction wave heading angle is going to be, if I take the dominant direction, is going to be this one, that is this angle. So, my wave heading is going to be from here to minus 90 degree to here to plus 90 degree. This is, see, this plus minus 90 degree is going to give me my total heading with respect to this, or if I want to do other way around, if I call this heading angle without that, again if I call it, say I call it mu star, but if I call it mu again, mu w minus mu s, this is my heading angle. So, I am supposed to find out response of the ship for heading angle ranging between mu w plus 90 degree minus mu s to mu w minus 90 degree minus mu s, because mu w will vary from this line to this line. See, obviously what would happen, I will take a mu w, well mu w star, what I mean this basically varies between mu w star plus minus pi by 2 minus mu s. This is the variation that I am going to have. That is very obvious, that whichever way you are looking at. Now, the calculation is very simple, you see, the calculation is something like this. For response RAO, same formula will apply. My 2D response RAO, what has happened? If I call this response RAO, I had initially, this is this, right, this was equal to, well, RAO square this is my formula earlier, right, and now what is happening, I want to have this thing 3D, this is 2D. It is going to be having omega e mu, this is going to be RAO, which is going to be a function of omega e into the heading into S square of that. This here, this mu is going to be mu W. Really the process is very simple. What we are trying to do now is that if you will see, what we are going to be doing is simply repeating the calculation. See, what is happening is that now I have got, again looking at this diagram, if I bring back, for a given theta, this thing. Okay. Now you consider this first case. I will go back to the case number 1. So I have got ship going this side. Okay. Waves range between, this is my dominant wave direction again, and wave range between this direction to this direction. What I will do? First I will take one direction, some direction here. Okay. So I know its heading angle, this angle. So I will take some value of mu, this is my mu W, some value. How much I will take? Obviously I will take mu W star, say minus pi by 2, that is this one. Then I will take mu W star minus 60 degree, like that I will take. So I know this. So therefore I know mu heading. Mu heading is of course mu W minus mu ship. This I know. In fact, I can make it, because it does not matter which side it comes. So I will, well, maybe not keep it anyhow. So I will know this heading angle, that is this heading angle. Plus, in fact, I can put up this also. This is nothing but mu W minus mu ship. So for that heading angle, I will find the RAO, square it, find out my S2D omega e into F mu, multiply that, then I will get spectrum for that part. So like that, if I do for all, then I will get the entire spectrum for all part. So this is exactly what is being done in the procedure. So it is absolutely pure algebra. There is just nothing to it. I will give an example, then we will be able to understand that. So in other words, what would happen is that we will be just doing that. So now this response is SI we call. No, actually we can call this. Let's call it. So we end up getting the response. Let me write response as SR rather than SI, because that's better. So SR see here, this mu we should write. Remember, the heading comes inside this. What is this omega e? Omega e is actually function of omega, v and mu. So this mu is actually, as a functional dependence I should write W, because the wave heading angle, because basically see this is nothing but mu wave minus mu ship. Mu ship is fixed. Remember, mu ship is fixed, going in some direction. With respect to xy coordinate, mu ship is fixed. It is mu W that is basically varying. So I can take this in terms of like this, okay. And this is what we find out is that this is S3D. Well, we can say S3D. No, RAO. This is what we have found out. So this is what we have done before, right? And of course, if I want to find out the area under that, if I integrate that, this integration is going to be 2 times because of this d omega d. I will end up getting what is called area. In other words, volume rather. My point of saying is that you end up getting the volume under the response spectrum, that is volume under, say I am going to get a similar response spectrum, each one I multiply with that, I will show that, then I will get the volume, and my response amplitude 1/3 etc., all of them will again become equal to say 2 m0 etc., etc. So, the procedure becomes just the same as 2D, it is just that you are going to be repeating it. So, it will go like something like that. You will start here, we will take mu w equal to some value, say in this example, let me take this example it turns out to be say this value mu w star is let us say 60 degree, okay. Then this first value is going to be minus 30 degree. So, I am going to have mu w is coming from minus 30 degree to 60 plus 9 150 degree, right. So, I am going to take minus 30 0 like that, I will do all that. So, here what I will do here, say for first one I will take mu as minus 30 degree, then what I will get mu ship, of course I know in this case mu ship is let us say plus 45 degree, say this is actually say 45 degree. So, I have plus 45, it is okay, let it be there 45 degree. Then of course, my mu heading will become minus 30 minus 45 whatever, that is 70 basically minus 75 degree, which is taken as 75 degree, because remember for a shape, for a particular shape, whether the waves come from this side or this side, plus theta or minus theta, they are same, because you are calculating RAO for 1/2 because of symmetry. So, this is like same. So, I will have RAO for that. Now, I will calculate this. So, I will have for this my so, I have this, okay. Then I have this this is 2D, then I no sorry this I can multiply this into directly, I can do here this f mu. See here what I do, remember for 75 degree I know the RAO, okay. For 75 degree what I will do, I will find out the typical that component. How? Because I know here what is my f mu, this I will find out, that is 2 by pi cos square theta, remember theta is 30 degree here, no sorry not 30, 90 degree here, sorry, because it is measured from this, the spread theta is actually this, measured from the main line, okay. So, I know this spreading function which is going to be 0 here. So, I know this, I will get this one. So, the point is therefore, I am just repeating this calculation, that is all, I am just repeating. So, that means my table 1 I am going to have say first table I will be taking, well mu s is always fixed, mu s is say again I will want to do this. Now, I will take here mu w equal to minus 30 degree f mu w, I will know what is the value, this value I would know it. So, therefore, for this particular one I calculate my so called S response, this I find out, okay. This I find out same way, the way we are doing previously, you know, like you have got omega A here, then you have got S 2D omega E here, then of course S 3D omega E mu here, because this is nothing but multiplying this with f mu, this value. See this value is multiply this into this one, straightforward, right. Then I have got RAO here for this, then I have got here SR, this is going to look like some small thing like that. This applies for mu w equal to minus 30 degree. repeat that for 0 degree. So, like that you will end up getting here. Earlier what we did, I did not have this as a variable, remember. So, what I had only, in fact what I had this, but I always had this same as 45 degree, because I have always assumed, not 45 degree, sorry, I always have this mu w as mu w star. That is, I always had the waves which is, all the waves were coming only in this direction. In earlier case, 2D case, all the waves coming in this direction. So, I did the calculation only for a one particular mu w star. All that we are doing here is that we are repeating the calculation for assuming wave to be coming from all direction, and for each direction I have got a 2D spectrum. But the 2D spectrum is a 3D multiplied by that function. For example, in this case, for the waves coming from this direction, my 2D spectrum is actually 0, because f mu is 0. So, maybe I should illustrate it even better, because I think there is some little confusion still. I will maybe I will elaborate slightly even better. The full step for a particular case of, let me draw some diagram for a case, just one particular case, it will be easier for us. Now, I will draw different color here. This is dominant wave direction, let me call. This is, the waves are going to be of course within this, waves are going to, once again I write like, anyhow I am going to take a particular, just a particular wave. So, this direction see, this is, I call this alpha. Okay. See what I am, just see, I want to go through this slowly once again then, because we are going to show only one case and then you can just repeat it. Once again, shape is here in an absolute frame of reference. You can, if you want, you can make this as x direction, but normally we do not do that. The reason is because when we want to, what would happen in nature, in a particular place, this direction would be fixed. For example, you would know from spectrum that there is a dominant wave in northeast direction, say between Calcutta to Andamans. Okay. So, this direction is fixed, but the ship might be heading north, ship might be heading east, the ship direction is arbitrary depending on which side it is heading. While going from here to Andaman, it might become heading south west, whereas southeast, whereas coming back it is to Calcutta, for example, it will become northwest. So, obviously, there is a direction change. So, therefore, this direction should be kept very well in my calculation process. That is why we are keeping this way with respect to absolute. You can consider x and y to be true north, true west, no, true east. Okay. So, you can say north, this east, etc., like if you want this north, this is east. Now, we are speaking for a particular case when I know that there is a mu star here, waves are coming here, my ship heading is this thing. Question is, find out the response. Now, I know from the spreading function that this wave is spread from this angle to this angle, that means from mu w star plus minus 90 degree. From here minus 90 degree is this angle, plus 90 degree is this angle. Now, I am now going to do the calculation. So, I took one particular, I have to repeat the calculation for all wave. So, let me say I am doing the calculation for this particular direction of wave. That means, I have a table here, first table, in fact I will start from here, but there will be number of tables, say table. So, I am calculating the spectrum for this, then for this, for this, for this, for this, for this, etc. So, this is my nth wave component, let us say direction. So, for my nth wave, let us say I have a for particular one, my mu wave is given by, well, mu wave is given, some mu wave is given, let us say whatever. So, this is going to be mu w star. In other words, I am doing this for, let us say alpha equal to, repeat this, minus 90 minus say 60 going to plus 90, that is what we are going to do. So, I choose one particular alpha between minus 90 to plus 90. So, I get mu w, I get mu w. Okay. Now, remember here my spreading function is function of which angle? It is function of angle alpha. So, my spreading function here is function of angle alpha. So, what I have got now here is the case that a table where I have got mu w star, this is constant, mu s, this is constant, and I am doing table number 1, number say not 1, say some x. So, for that I have alpha equal to minus say 60 degree, which of course referred to mu w equal to some value. So, I am doing this for this alpha equal to minus 60 degree. Remember, I have to do from minus 90 to plus 90. So, now I have got this. So, I now know what is my f alpha. So, here I am having this. Now, my alpha, which is my wave spreading or whatever you can call mu, that is the basically this is the wave, well actually I call that mu in my earlier cases, where in fact we call this to be, we call this alpha as mu in other cases. So, this is my wave heading. Once again you see what is happening, my wave is here, my shape is here, no again I sorry no alpha is alpha only. So, basically mu is going to be essentially this angle, that is here to here, okay, that is mu s minus mu w. This is going to be, so my wave heading is mu s minus mu w. So, there are two, this is quite the problem, my this is mu s mu s minus mu w, but what is mu w? Mu w in my case was mu w star minus alpha. So, this was basically mu s minus mu w star plus alpha. So, this is a function of alpha. So, for a given alpha, therefore, I have got alpha equal to something. So, I have got mu equal to something. So, my table now has alpha equal to something. So, I have got mu equal to something. This is my angle for the spreading function, because spreading function is connected to angle measured from the wave to this, that is alpha. Response is connected to angle of that wave from the shape, that is this angle, or if I were to put this way, this is my this mu s. Mu s is on which the response depends, alpha is on which the spreading depends. Alpha and mu s are obviously connected to mu w star. Okay. So, all these are kind of connected to each other. So, therefore, what we are going to do is to repeat that. So, I have got this a particular angle alpha minus 90 or minus 60 I said, therefore, I find out mu s. So, I have got alpha. So, from alpha I get, I will find out the mu, that is heading. So, spreading is f alpha, RAO is RAO omega e into mu, okay, and mu and alpha are related, because what we find out is this thing, basically mu, this is what we have written now, mu equal to mu s minus mu w star as alpha. This is fixed, so this is fixed. This is fixed, so this is fixed for a given case. So, I have mu and alpha fixed. Now comes the very simple thing. So, for this particular case, I once again if I have mu star given, I have mu s given table 1, I take alpha equal to minus say 60 degree, thus mu equal to some number I will get, okay, fixed. So, now for this particular mu I have now the calculation, I have S2D. Remember this omega e also has to be done. Remember this is another important thing. Remember that this transformation has to be done, right. This 2D to encounter spectrum, and here comes another interesting problem, because what would happen for a particular mu. See, I have no choice. See, when I take minus 60 degree, I have this mu there. So, this might become a following wave, it may be a following wave. So, when you do a 3D spectrum, there is a chance that you end up getting a following wave, okay, even if the dominant direction is not following wave, because of this spread 90 degree plus minus spread, some component might become following wave, okay, which I show that to you later on in a minute. So, here there is a chance of remember that this transformation, this omega e, what is this omega? Omega e equal to omega 1 minus omega v by g cos mu, or cos mu is being the that wave heading angle. But this heading angle mu we have seen is mu s minus mu w plus alpha. So, I do not have a control. Remember this transformation is not constant for all. So, I will be choosing one particular alpha, for that I get what is my wave heading angle, what is my spreading function. Therefore, I have this transformation. This transformation may not be necessarily, this transformation may turn out to be as equivalent for following waves, because it may turn out that this particular alpha as you chose, this value has turned out to be equal to more than between 0 to 90 degree. That is possible, because after all whatever heading you will understand, the heading will also be overall spread over a radius of pi. This mu, range of mu will also be pi, because you are after going from one side to other side. So, there is a chance of its becoming some component following waves. So, you have this. From there, next I multiply this with f, in this case f alpha, that spreading function. So, I end up getting this which is S2D into f alpha, then I have RAO, then multiply that to I get S3D response for that particular alpha. Okay. So, this I will repeat it, and when I repeat it I will end up getting the graph. So, it will look something like this therefore. So, for example, we did that, I will just show it to you. It may look something like I just show a particular, yes, it may look ultimately something like this. This I do not know how I can put that picture here. The RAO may look ultimately, you may end up getting a look like this. The spectrum may look, response spectrum, very difficult to plot it. I mean, what I mean is that what is happening is that this is my response, like no, actually it is not that way. I will put it this way. This is my RAO, let us say, what we are plotting RAO. See the RAO, you will be putting the RAO for over the entire like spread of a particular, see this is my pure RAO, because I would have calculated RAO. See, I will need now this tells me I would basically need to calculate my response amplitude operator right from 0 to 180 degree. However, not all waves might be existing. Typically, this 3D spectrum therefore requires me first to pre-calculate RAO for 0 to 180 degree. Why 0 to 180 degree? Because symmetry tells me that 0 to minus 180 degree is same. So, I will have the entire 0 to 180 degree, saying that for any angle mu heading angle, I know the RAO. So, I must calculate my mu, the RAO for all angles. Okay. So, this is our typical RAO given. Now, this picture again, see if you see. So, I have my RAO, that means whichever direction that my wave comes, I know my response. Comes the second step, I chose spectrum number 1 with a dominant direction here. Then I know this spectrum have waves coming from this angle to this angle. So, I will find out RAO for this angle when I chase. Then I repeat that calculation. So, what would happen is that ultimately I will end up getting a series of graph for different angles. So, I will end up getting basically SR, the response for different angle alpha, you can say here we call alpha, we can call anything, this alpha being the angle of the wave with respect to the dominant angle, that is this one, that is this one, this with respect to the wave the alpha. This alpha would be ranging from minus 90 to plus 90, and I would have been doing this for say SR omega E for say minus 90, then minus 60, minus 30, 0, like that. For each one therefore, I will get the spread. I can always plot this graph. The more important thing is that then I will find the areas. So, what I will do, I need to find out this volume under SR omega E alpha d omega E d alpha obviously this is very simple. So, I will essentially do this each one, then it is like your displacement calculation. No, we find out for every section the areas and then add the sections for get the volume. So, you first find out this for each one. So, for each one this picture I wanted to show this picture, this it comes out in a short form, it will come out like that. For a particular angle I will end up getting this. Let me say that this is my essentially this wave. This is for alpha equal to minus 90 degree. Then I have, well, of course, here will be like that, you repeat. See what I have done here, if you look at that, you are getting for a given minus alpha, First of all, remember I wrote it in one step, but there are more than one step involved. First of all, you have to find out, well, 3 steps involved, S2D omega. Then see, for getting this one, first I have got S2D omega, that is look that like that. Then I have got S2D omega E. Then I multiply that with F omega or F alpha to get this one. So, this itself has got 3 steps. So, well, maybe that I will just show this one again. So, what is happening here, to get this I have got S2D against omega. From there I end up getting actually there is not a graph here. Then let us say, then see, this F alpha is a number, no, see, for example, cos square 60 is how much? Cos 60 is root 3 by 2, so 3 by 4. Okay, cos 60 is 1 by 2, right? So, it's 1 by 4 then. So, whatever 2 pi. So, you know this, right? What my point of view was, what I am saying is that, see, this particular one is therefore this one, this is a graph is the one that you are plotting here. This is the graph you are plotting here. Remember, getting this graph involves your alpha. Alpha is involved in this transformation, is this transformation, this to this. What all angles it involves? It involves not only alpha, also ship heading, because connected to ship heading this omega E comes out. Omega E is equal to, like basically this is a function of mu, and mu is a function of mu S, mu W star and alpha. So, all are involved. So, you just have to keep your mind straight, that is all. All I am trying to say is that the procedure therefore is absolutely algebraic, there is just nothing to it. Only what we are doing is we are repeating the graph, going back to this very first diagram, that all that we are doing is now is very straightforward. I would be knowing for each spectrum, for each angle, this one is for example here, this is for 30 degree, this is for 30 degree of angle alpha, like that. Now, I would find out, I will choose this one. So, I know f theta, but then I will find out this causes what heading angle with respect to ship. That means, these waves are coming at certain angle to the ship, say 45 degree, then I will choose RAO for that particular 45 degree, use omega E for that particular waves, then I will find out the spectrum for that, then I will get response for this, like that I will go. In other words, what is therefore happening, my ship is travelling here, one set of waves are coming this way. So, I will find out what is the response. Second set of waves are coming this way, I will find out that. Third set of waves are coming this way. So, like that I will vary this right from here, this is a dominant direction somewhere here, right from there to there. So, I will choose this, I will choose this, I will choose this, I will choose this, each one I will choose wave coming, that is all, there is nothing to it. And therefore, now the question is that when I do that, you see that I cannot avoid sometime following waves, very simple reason. I have the ship going this side. Now, let us consider this case, in this particular case. So, if I had dominant wave is head wave, dominant wave is head wave, then my waves would be coming right this direction, this direction, this direction through this circle. Okay. So, here what is happening? I have actually all the angle heading angle between minus pi by 2, well actually if I come this side, well the angle is 180 minus 90 to 180 plus 90. So, it is all head C condition, but suppose any other angle, see this is the point, any other angle, supposing I had the wave coming dominantly this direction, what has happened therefore? My waves are spread over this angle, this. So, when I consider this angle, see this particular angle, my shape is here, my wave is coming this, say this particular one. Okay. So, my angle is less than 90 degree. In fact, you can, therefore, what I am saying, what my point of saying is that when I take 3D spectrum, okay, then necessarily if my dominant direction is not 180 degree, because after all if dominant direction is 180, in other words if you look at this mu is equal to mu ship minus mu w star plus minus pi by 2, this is by range. So, if this one is pi, then I end up getting pi plus minus pi by 2 is how much? Pi plus pi by 2 plus this head C. But if this is anything beyond pi, anything else than pi, I always will have an angle which is having a value between minus pi by 2 to plus pi by 2, which means which will have a following wave condition. Right. For example, once again if for example dominant wave is beam direction, so this is another way of looking at that. See, if my dominant waves were coming this side, that is dominant wave. So, what will happen? There will be some wave this side, some wave this side. You see here I have getting a completely following wave, one component. The dominant wave is this side, I will get wave from here up to here. So, this is the reason why, although I said when I was talking about 2D spectrum that look the 3D spectrum transformation, that is omega to this is following wave, and in a head wave head wave following wave it can become very funny. I was saying we do not pay much attention to that, but you know if we have to do an automatic program, you are writing a code or something, you are doing a calculation for 3D spectrum, then what would happen? You would normally feed the dominant angle as input data, you would feed the ship angle as input data, or you may also call, sometime you may, if you want, you may feed the dominant angle with respect to ship as input data 45 degree. Immediately you find out I have some waves which is actually 45 minus 90 to 40, that is 45 degree itself, that is a bow stern quartering wave up to the bow quartering wave. So, I cannot avoid doing following what I should say, a spectrum for heading angle which correspond to following waves. So, the shape, as I said yesterday, one of the component therefore in case 1. So, I have component 1 when alpha, if once again if I take minus 90 degree, I end up getting a spectrum shape which look like that, but when I take alpha equal to plus 90 degree, then I end up getting a shape which is nice. This is my SR. Okay. Then what is happening? Remember, I have to find the area under this and also area under this, because I need the volume. So, I may end up getting problem here, because I have some singular values coming, and that is exactly why I was trying to tell that we could use for such cases integration over omega domain. That is much better to take integration over omega domain for finding area. So, there is no avoidance of actually knowing how to handle the spectrum in following wave condition, if you are going to determine response in 3D waves. Okay. So, this is one point that I wanted to make. The other point is that, which I said yesterday, that you see, look at this volume part, once again this volume part. Now, response spectrum is going to look something similar to that, because you are multiplying responses. Now, what is happening if I were to take only 2D spectrum? So, my 2D spectrum would have looked a graph which would be this one only, but higher. Remember, this is not getting pushed down, right. Now, suppose my response, but I am doing it for different mu s. So, at a particular mu s, my response is higher on this side. After all, I am doing for, see, I am doing the responses for mu s equal to 0 degree, 10 degree, 20 degree, etc. In one particular case, what would happen? The mu s will be such that my response RAO is very high. After all, response RAO also keep changing with respect to angle. The simplest example is beam waves roll. You would expect that if obviously the shape is like that and waves are coming this side, you expect the largest roll. So, roll you expect high if heading is pi by 2, right. So, now what is happening? Let us take roll as an example. If I were to do a 2D spectrum calculation, I am presuming all the waves coming from this side and I have a very large roll. So, I end up getting an estimate of roll, say whatever roll 1/3 or whatever, some value say 15 degree. If on the other hand I were to take this as a dominant wave direction and wave coming also from here and here, remember, see, remember in this case I will have wave coming this side, but also some wave coming this side, some wave coming this side. Now, these two waves do not give roll at all, because they are coming exactly symmetric direction. So, therefore, what happened? The one that is giving roll high is less in number in the 3D wave. So, what would happen if I take the volume? I will end up getting the roll which would be probably less than that 12 or whatever, maybe around 8 degree. So, what happened? If I were to use a 2D spectrum, my prediction is that there is a case or direction of waves in which my roll maximum is become 12 degree, 1/3 roll maximum. If I take on the other hand 3D spectrum, I find out that the maximum roll considering all angles is 9 degree or whatever. Therefore, 2D spectrum normally ends up giving me higher estimate. You may say, why should I go for higher? But that is a different question. But you know that normally that is what is obvious. This is one of the reasons what I mentioned yesterday, that 2D spectrums are used. But having said, some people want to do 3D spectrum. Now, we learn today and that 3D spectrum calculation, as far as calculation is concerned, is nothing but sum of 2D spectrum. Somebody told me long back, you know, that this I will end this thing by that. Say if supposing a function there, say let me call it y, is a function of x, you need only one graph. If it is function of x1 and x2, you need series of graph. If it is x1, x2 and x3, what you need is same thing repeated. So, this is what has happened in my 2D case, it was function of omega mu v, but v is constant. So, what happened for this 2, I need one graph, but now what happened, I have to repeat that for different angle also. So, that is it. So, my 2D spectrum is page 1 and 3D spectrum is going to be number of pages. So, simple algebra, nothing to it. So, with that I am going to end this 3D spectrum motion in 3D spectrum part. Thank you.